Hi everybody, welcome back. So we're going to do another much more involved problem this time. It's going to deal with both shock waves and expansion fans. So you're getting it all right here. You're going to get so much experience here. So let's do it. So what you're going to have is we're going to have an infinitely thin flat plate. Why infinitely thin? Because it makes this a lot simpler than if it wasn't infinitely thin. And it's at an angle of attack of 16 degrees. Okay. Now what we're trying to figure out is it's in some sort of supersonic flow here. And that flow is going to be, let's have this be 2.6 degrees. No, sorry, Mach of 2.6, goodness. Yep, Mach 2.6. Now, what we're going to try to find this time, and this is going to be something we don't do all that much, is coefficient of lift and coefficient of drag for this flat plate. Now let me go ahead and give you an idea of what's going on. Now, we already know how lift and drag works. So if I was to look at this guy right here, what I'm going to realize is I'm going to have some sort of expansion fan on the top, and I'm going to have an oblique shock wave on the bottom. Now, shock waves increase pressure. So this is going to be, I'm just going to say high. And this one over here is going to be low. So we're going to have a low pressure on the top because that's what expansion fans do. It lowers the pressure. I'm going to have a high pressure on the bottom. And so then if I can figure out the difference between those two pressures, I can figure out a force. So more or less, I'm going to have some force, which I'm just going to put this direction like this, because it's going to be higher on the bottom. And it's going to be more or less P high minus P low times an area. Okay, so that would be the force there. Now, lift is always in the up direction. Drag is in the back direction. And so if I can then figure out my angles, using this force I just calculated, I'm able to find out what my coefficient of lift is and my coefficient of drag is. So that's the basics of what we're going to do. Now before we can do any of that, we're going to have to figure out our pressure in both of these sections. We have to figure out our pressure in both of those sections. So let's get right on that. Now here's the thing. Your problem doesn't actually give you a pressure. And if you're wondering why it doesn't give you a pressure, it's because you actually don't need it. It's completely beside the point in this case. Now, how does that come out to be? Well, I'm going to go ahead and tell you that when you get to coefficient of lift and coefficient of drag, what we're going to need at some point along this line is we're going to need ratios, like P3 over P1, with, let's see here, this being 3, and this being 2, and this being 1 over here. Or we're going to need, P2 over P1. We're going to need those ratios to find the coefficient of lift, not the actual pressure. Because the pressure is beside the point. It just changes, and it's going to be changing whether I have it be 0.5 to begin with, or 1 or 2 or 3. The amount it changes is going to be a ratio for the expansion fan and the ratio for the shock wave. So I don't really have to worry about what the actual pressure is. Okay. So now I got a little bit of setup here. Let's begin figuring out our information for section 2 and section 3 right here. Okay, I'm going to get rid of this because I'm going to need a little bit more space. That'll help me out. Now, as always, I'm going to be doing this step by step by step by step. And let's see here what we're going to do first. Let's deal with the shock wave first. Okay, so oblique shock wave first. So we have a Mach 1 of 2.6. We have a deflection angle of 16 degrees because that's equal to my angle of attack. It has to turn the same amount. And so that means that I'm going to have to go to my theta beta Mach diagram. This guy with theta is equal to 16 degrees, and my Mach number is going to be equal to 2.6. Okay, let's go figure out what beta is. That's what we need to find out. And so now with the power of moving magic, I'm going to jump to that diagram. We're going to do every single step. I'm going to show you every single appendix, every single diagram, just like last time. Cool? Okay, here we go. Now I've jumped over to our textbook, and I'm going down to in section 9.2 where you find this diagram. As a note, I'm pretty sure that most problems just give this to you, but I always want to show you where it is in your textbook, just in case you don't know. Okay, now let's go ahead and grab a screenshot so I can draw on this. Also, so I can just zoom in a little bit because it is a small diagram. I really wish that we had like a bigger version of this, but they have not done the best job of it. Now, I've got a Mach number of 2.6, so that's right in here. Okay, and if you're wondering if it's a weak shock or a strong shock, in almost every case we're going to deal with in this class, it is a weak shock. Unless it tells you it is a strong shock, go ahead and assume it is a weak shock. Now what I just did there is I just went ahead and traced that line because I find it easier to do that. Now I've got to find my deflection angle, which is 16. Thankfully it's right on the line. Okay, I go up this line right here. Okay, I hit. And ooh, that is pretty perfect. It goes right across on this line. There we go. Now there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. And it's 10 right there. So that means that's 39, 38. That would be 37 degrees right there. Okay, 37 degrees. I have my values. That works out pretty well. So let's jump back to the problem now because that's enough to start us off on our shock wave. There we go. Okay, now we found all the details we need for our oblique shock wave. And so now we have to turn it into like we're looking at a normal shock wave. How do we do that? We find the normal component of our Mach number. So remember that my normal component of my Mach number, goodness, blah, for this one is going to be equal to m1 times sine of beta. And so it's going to be equal to 2.6 sine of 37 degrees, which should come out to be 1.565. I'm just going to go in 1.5. Anyway, I'll write it all the way. I'll write it all the way because it might work out perfectly that way. 4.7. If you're lucky, the textbook manufacturer decided they didn't want to have to interpolate, and so you won't have to interpolate. If you're unlucky, they decided to actually do some work today. So what we're going to do right now is we need to go and find the pressure ratios because it doesn't really ask for anything. We don't care about temperature really for this. We're going to use pressures to find out everything. And so we need to find what P3 over P1 is for a Mach number that's equal to 1.5647. And we're going to go to Appendix A, which is our normal shock appendix. Because we turn this oblique shock wave into a normal shock wave by finding only the normal component of our Mach number. Okay, let's go find out what P3 over P1 is then. So I'll just jump back to my textbook here. I still got this up. I'm going to go ahead and close it down. And we're going to go over to Appendix A. There we go. Wait, sorry. That's the wrong one. I'm in Appendix B. What am I talking about? I want the normal shock properties. Goodness. Failing at life today. I apologize. There we go. That's better. Okay. So here's my normal shock properties table. I'm going to go down as far as I can. So I got 1.56 right here. And let's see. I've got 1.5647 there. Ugh. It's not quite perfect. But you know what? It's close enough. We're going to just count it and say it's good. So I'm going to go ahead and screenshot again so you can see exactly where I'm getting the information from. Here is my Mach number, 1.56. And here is my pressure ratio, which I'm going to say is 2.673. It is slightly off there. I could interpolate to get a slightly different number, but honestly, it doesn't change too terribly much in that small amount, so I think we're going to be completely fine. Okay, so 2.673, let's go ahead and write it down in our problem statement. So I'm going to run out of rooms, and that was supposed to be Appendix B. I knew which table I need to go to, just the wrong letter. There we go. 2.673. Okay, that's going to come in really handy. We're going to need that a lot for this problem. Okay, let's see. What else are we going to need here? Well, let's deal with the expansion fan now. Okay, let's deal with the expansion fan, because that's going to be very, very helpful to us. Okay, so expansion fan up here, we have a Mach number of 2.6, and so we're going to have to go to our Prandtl-Meyer table in Appendix C to figure out what it is. Okay, so You know what? To help ourselves out a little bit, I think I'll stay up here. No, I'll go down. I'll go down again. Okay. So let's put a little line here and make sure that we know this is now working on expansion fan. Okay. So first off, we have a Mach number, 2.6, and we need to find out what our first Prandtl-Meyer function is. And so for that, we're going to go to Appendix C. Appendix C. And it shouldn't be too bad to look up. I'm not too worried about it this time. So let's continue on. Okay, so we're back in our textbook, Xing out of this because I don't need that appendix anymore, and jumping over to Appendix C, which honestly is my favorite one. It's pretty easy to deal with because you only got 3 columns here. You've got the Mach angle, you've got your Prandtl-Meyer function, and you got the Mach number. So I'm going to go down to 2.6, which is way down here. Nice, got an exact number there. And I can see right there my angle's going to be 41.41. I'm going to go ahead and screenshot it again, though, just because I'm going to be completely crazy and continue to show you every single step of the way. So here is my Mach number. And this right here is my Prandtl-Meyer function. Remember, that's a times 10 to the second power. I multiply that by 100. So I get my first angle is going to be 41.41 degrees. And getting the second angle is super easy. Not V2 squared, goodness. V2 is equal to V1 plus my deflection angle, which is the same as earlier. So it's going to be equal to 41.41 plus 16 degrees. That's going to be 57.41 degrees. Okay, so that looks good. But now what I have is I have my Prandtl-Meyer function, and I have to go back to the tables to figure out what my Mach number is after the expansion fan. Because remember, it accelerates, it should get bigger. If it gets smaller for some reason, that means you made a mistake. So, and what's my Mach 2 going to be equal to? I don't know, let's find out. Can I see it here? I did not give myself enough space. Rats. Well, it's not too difficult. I'm going to go down a little bit further and find it. If we get lucky, we'll have one that's exactly on the line. We didn't get quite lucky here, but we did get pretty close. You know what we're going to do? We're going to actually interpolate this time. Why? Because I don't show you interpolation all that often, and so I want to show it to you now. Let's go ahead and get it done. So first off, we had an angle of 57.41. It is really close to this guy right here. I could say that it's 3.45, and I would be very, very close to the correct answers. If you want to skip this, you can, but I do want to show you how to interpolate. Now, interpolate, what I need to realize is that my value is somewhere in between these two right here. It's not either one of those. And so what I'm going to do is I'm going to make an interpolation sandwich. I'm going to take a box. This is all the data I'm going to need, because I want to know my Mach number, which I know is in between these two. I'm going to use my Prandtl-Meyer function to find that. Okay, so let's go ahead and write out our equation, and I'll start filling in the numbers. So here's how my equation always goes. It's the same every single time. So my Mach number is going to be equal to m low plus Prandtl-Meyer function minus Prandtl-Meyer function low times m high minus m low over Prandtl-Meyer function high minus Prandtl-Meyer function low. Now, you get to name what the low and the high are. I can call this top row low. I'll put a little L. It's not one to write right now, so it'll probably appear in a second here. Erase, draw. There it goes. See, I knew it started appearing. So let me erase now that it's all popped up suddenly. There we go. So I can call this top row low and the bottom row high, or I can reverse it. It does not matter. It's just whatever you call low, both of these values become low. Both of these values become high. You have to keep them connected. You can't just switch things willy-nilly. But the rows themselves, you can name them whatever you want, and you can flip it and you'll still get the exact same number. Okay, so let's go ahead and start plugging those numbers in. So let's make sure I do this right. So m is going to be equal to 3.4 plus 57.41 minus, what's that number? Jumping back again, it is 56.91. Okay, 56.91 times 3.45 minus 3.4 all over, this was 56.91 still, and I need to figure out what m high is because I didn't memorize it. I think it's 57.76. Am I right? 57.73. Right here. That's the value I'm looking for. $57.73. Now, if I plug all this in my calculator, what I get is that my M2 is going to be equal to 3.4403. Okay. Now here's the thing. When I'm going through my oblique shock tables, like if I know my Mach number, I also know some pressure ratio. What you realize here is that if you look at the expansion fan appendix, you don't have that. Like it gives you three things: Pronomeyer function, Mach number, and Mach angle. No pressure ratios. We need those pressure ratios. So where did they come from? Well, remember that an expansion fan is an isentropic process. So I can go to my nice isentropic tables to help me out here. So let's do that. Isentropic means appendix A. So I need to get pressure ratios. I need pressure ratios for this problem. Okay. Going back here. And let's jump to those tables. Appendix A, looking good. I'm going to go find a Mach number of hopefully 3.44. Really having to scroll down here quite a ways. And there it is, 3.44. Oh, goodness. Okay, well, I'm going to go ahead and help you out here. I'm not going to bother to interpolate this time. I did it last time. But let's go ahead and see the data and go from there. Sometimes I'll be willy-nilly and say, it's close enough, but in these cases, it would be better to interpolate because it's more or less halfway in between these two. Okay, so this is the data I need. Now, if I go to the heading right at the top, you're not going to see static pressure over some other pressure. What you're seeing here is my total pressure over my static pressure. And so I'm going to have to remember that later. Now I'm going to interpolate. I'm going to get something between these two values. And I'm going to go ahead and tell you what that value is so we don't have to calculate it right now. So for a Mach number of 3.44, what I get is that my P02, so my total pressure over my static pressure is equal to, where is it? Yes, 70.0774. Okay. Now this is where you panic. How am I ever going to get what I need? Because this is total pressure and I need static pressure ratios. You do. You totally need static pressure ratios. So we're completely doomed. Nothing we can do. I'm kidding. We're going to be fine. We're going to be fine. Now let's look at what we want, and we'll go to what we need to find to get what we want. So what I want is P2 over P1. Okay? I really want that. Now, I don't have that, but what I do have right now is, well, I have like, okay, P2 over P02. That's, I know I reversed it, but you can see that's there. So I got a P2 on top. And so I can find something with attached to a P1 that can cancel out the P02, I'd be good. Now, when I did my last expansion friend problem, we actually had a very similar example to this. I was trying to find my pressure after the expansion fan. This is exactly how I did it. And what I learned is that because it was an expansion fan, my total pressure is actually constant. So P01 equals P02. So if I look up this value in my isentropic flow tables, which is really easy to find, I can find my pressure ratio. Okay, so let's go ahead and do that. We're going to go to our expansion appendix A again. And this time we're going to look for a Mach number of 2.6, because that's my initial Mach number. And what we're going to find is we're going to find P01 over P1. So let's go back to that table and find it out. This is a nice, easy one. I can even still see it right here. It is right up here. That's 2.6, my Mach number. Here is that ratio I needed. And I still have it on that page, which is wonderful. And so I bring it back. And so this is going to be equal to 19.95. Okay, now that I have that, I can figure out what P2 over P1 is equal to. That's going to be equal to 1 over 70.0774. That is the inverse of my P02 over P2, which I got up here. I'm going to multiply that by P01 over P1, which is 19.95. And if I'm looking at this equation, these two cancel because they are the same thing. Okay, they're the same thing for an expansion fan. And so that gives me a pressure ratio of 0.2847. Okay, I've got P2 over P1. I have P3 over P1. It's looking glorious. And now you're thinking to yourself, okay, we've got all these pressure ratios. Where in the world are my coefficient of lift and coefficient of drag going to come out? Well, it's not so bad. Let's just look at the definition for coefficient of lift, okay? So first off, CL, coefficient of lift, is equal to my lift per unit span. Gotta make sure I'm doing this good here. Try my best. And let's see here. There we go. Times Q infinity. And then multiplying that by S. Okay, so dynamic pressure, my relevant surface area right there. And you're like, wait a second, this is per unit span. So what this goes from is it goes from being a rectangle down to a line. Like what part of that line is actually in the lifty direction. So I was looking at my wing from the side here. I'm only going to be looking at it like thinking about the chord because this is infinitely thin. I have, this chord line right here. And there's a portion of that that's going to be causing lift. So my flow is just going straight in here. The portion of it that's causing lift is going to be this area right here, so this length. While the portion that's causing drag is this length, just breaking up into vectors. So that's what's going on right there. I know it's not always completely straightforward. Okay, now let's figure out our lift and everything else and see how we can go here. Okay, I think this is looking good. So first off, my lift prime, that's going to be equal to, first off, I have to multiply by my pressure. So I have P3 minus P2 because the pressure on the bottom is going to be greater than the pressure on the top. So it's going to be pushing it up. Okay. And then I'm going to have to think about what my chord is going to be because force is equal to pressure times area. And so that's going to be my chord times cosine of alpha. So this is that component of the chord that is actually in the right direction. Going back to it again, here is my alpha. Cosine of alpha is the portion that would be pushed up by air. This line right here. And we have some unknown length C, which we're going to find out doesn't actually matter too much. I'm going to rewrite my cosine a little bit because that was not good handwriting. Okay. Now, I've got all that. Now I got to do Q infinity and then my relevant area. Q infinity. The relevant area is going to be equal to, my chord times 1. Why 1? Because I'm saying it's a unit span. And so the span I'm dealing with is 1. So if I simplify that, I get P3 minus P2 cosine of alpha over Q infinity. Now this is great because you see our chord disappeared. We still have our angle of attack, but we know that. So dynamic pressure. Let's focus in on dynamic pressure next and see if we can find a way of getting rid of that guy or putting it into terms we can deal with. So first off, the dynamic pressure of the free stream is simply going to be equal to my dynamic pressure before the shock waves. So we can call that, like, for the section 1. That's going to be equal to 1/2 times my density initially times my velocity initially squared. Now here's the thing, we don't actually know our density beforehand, and we don't know our velocity beforehand because it never gave us a temperature or a pressure. So this is hard, all is lost, can't do anything about it. End problem. No, we're not going to do that. I'm messing with you. It's okay, we can figure this out. Okay, now what we're going to need to do is we're going to use some of our relations for the speed of sound to get rid of our density and then to get rid of our velocity. Okay, now, do you remember what our speed of sound was equal to? Well, maybe you don't, but let's go ahead and use that right now. Now, what we probably remember is that our speed of sound is equal to the square root of gamma RT. I could also rewrite that as a squared is equal to gamma RT. Now, we don't know temperature. We don't know, well, we know our specific gas constant. That's pretty easy, but we don't know temperature. However, remember, pressure is equal to density times RT. Wait a minute. Therefore, pressure over density is equal to RT. Now I'm going to plug this back into here and see what happens. So what I get then is that A squared is equal to gamma times pressure over density. I think you probably see where I'm going here. I have a density right here, and maybe I can use that to help myself. Okay, so what we're going to do is we're going to use this relation to help ourselves out. What we're going to do is we're going to multiply the top and the bottom of this guy by gamma P1 over gamma P1. Now, that's just multiplying by 1. I'm allowed to do that. That's completely fine. And so what I'm going to get from that is the following. It's going to be equal to, make sure I do this right. Yes, I'm doing okay. 2 gamma 1 P1 times P3 minus P2 cosine of alpha all over density 1 gamma 1 P1, there we go, times V1 squared. Okay. Now, if we mark it out right, if we're careful, what we can then find is our speed of sound, which is going to be equal to, make sure I'm grabbing the right stuff, this guy, let's see, yes. That should do it, yes. So that would be equal to taking this guy, and this guy. There we go. So those three together will make my speed of sound. And so what I'll then get, if I do this right, I'm careful, is I'm going to get 2 times A1 squared P3 minus P2 cosine of alpha over gamma 1 P1 times V1 squared. Okay, now what is my velocity over the speed of sound? Well, we know that our Mach number is equal to our velocity over speed of sound. So that means that this is going to be equal to 2 times P3 minus P2 cosine of alpha over gamma 1 P1 times the Mach number squared. Beautiful. Beautiful. That's looking good. And what that means is I then have all my pressure ratios. So I can then write this one more time, now with our pressure ratios, which we already know, to be able to solve the problem. Now I'm not going to bother plugging in the numbers, all this again. I'm just going to go ahead and let you know that if I plug this in properly, what I'll get is 0.4852. That is my coefficient of lift per unit span. Okay, now that is looking great. And you're like, oh my goodness, we have so much to do now for drag. No, you don't. It's honestly really super easy. You know this is cosine. To get drag, we just change it to sine. That's it. So coefficient of drag is the same exact thing. I'm just going to go ahead and write the equation one time, and then we'll go from there. Okay, so everything else is the same. But now, sine of alpha. If I wanted to, I could actually write this in even more simple way. It just simply says that the coefficient of drag is equal to my coefficient of lift times sine of alpha over cosine of alpha, or tan of alpha. And if I plug that in, what I get is I get 0.1391. There was a whole bunch here, but we did it. We got it. And hopefully I was able to explain every single step to you in a way that made sense. Biggest thing is pressure ratios. We had to find those pressure ratios. That was probably the hardest part. And then it was just realizing that we didn't need to know temperature. We didn't need to know the actual pressure or even the density to solve for these drag and lift. All we needed to know was the pressure ratios and our Mach number. And the Mach number took care of so much for us. Well, that's it for this time. Thank you all for listening. I'll see you all later. Bye-bye.